All right, so let's get started. So I want to thank Aobo for agreeing to give this talk on very short notice. So we're looking forward to hearing his presentation about AI in rare event searches. So please take it away.
Okay, yeah. So first I want to thanks for Kate for the intro and the invitation. So today I'm going to tell you a little bit about my work in the region of AI in rare event search. So I'm a new faculty at Halijiolu Data Science Institute and Department of Physics at UC San Diego. So I just joined the A3D3, I think, a few weeks ago. So I'm very excited to share with all of you about some of the research I have done in the past and also some of the future kind of prospect about the research I want to do. So the title of this talk is called Fast and Slow AI in Rare Event Search. So I'm trying to split my topic into like 3 different regions. So the first is like the slow region where we talk about like what is a rare event search. So second is the fast region where I talk about some radiation detector and some of the AI algorithms we developed for it. And the last is kind of like overlooked section where I talk about fast for slow. That is how we can leverage the real-time machine learning or fast machine learning that we are all interested in here to benefit rare event search. So let's start from the slow session. What is rare event search? We know that high energy physics has been one of the pillars of the A3D3 Institute, and the 2 major experiments that many of us working on include the Large Hadron Collider, the CERN LHC, and the Dune Deep Underground Neutrino experiment. So there is actually some common things between these 2 experiments in that they actually both use some kind of generated signal. So for example, in LHC, we have this high energy particle beam, which are generated by this accelerator, and it produces about 600 million collisions per second. And in Dune, we have this so-called TIP2 neutrino beam, which produce like trillions of neutrinos per second. But besides those kind of generated physics signal, we also have some naturally occurring physics signal, for example, neutrinos. So neutrino is is actually amazingly ubiquitous just among us. So while I'm sitting here talking to all of you, there are about 10 to the 12 neutrinos generated by the sun that's penetrating through my body like every second. Although there are so many neutrinos that's like just floating around, they actually rarely interact with the rest of the world. So although there are so many neutrinos that's being produced every second, throughout my entire lifetime, there are only going to be like 2 or 3 neutrinos that actually scatter off of the atoms in my body. So it's extremely rarely interacting with the rest of the world. So that's why neutrino was actually one of the topic of rare event search back in 1950s. And there is this famous experiment called the Cohen-Ring neutrino experiment. It was actually the first detection of this particle, so this so-called neutrino particle, via a special decay called inverse beta decay. So this process is basically an anti-neutrino collider goes into a proton and it produces a neutron and a positron. So this interaction actually has a very, very low cross-section because neutrinos rarely interact with other matters, but it has a very unique signature because this positron, which is an anti-particle of electron, could annihilate with electron and produce some photon. So that's the first signal. And then just shortly after that, this neutron could got captured by a nucleus to produce another photon. So we have what we call the prompt signal here and the delay signal here. So if you combine these 2, you have a very, very unique signature. So this Cohen-Ring neutrino experiment was, as I said, was the first detection of neutrino, and it actually got the Nobel Prize in 1995. So nowadays, just seeing a neutrino through, say, inverse beta decay is no longer a very exciting topic. So it's no longer rare, or in other words. So what kind of rare event search we are doing in 2023? Well, so that's so to talk about this, let's first talk about the nuclear decay process called double beta decay. So double beta decay was first proposed by Maria Goldberg-Mayer in 1935. So basically, and it was detected by Elliott, Han, and Moe in 1987. So basically, this process is in certain radioactive nucleus, you have 2 beta decay that happens simultaneously, emitting 2 electrons and 2 electron antineutrinos. Because neutrinos rarely interact with the rest of with matter, so they will just escape your detector without being detected. So if you measure the energy of the 2 electron, you will see this kind of continuous kind of blue spectrum, as you can see on the right plot, because the 2 neutrinos could carry away an indefinite amount of decay energy. So this decay itself is extremely rare. Its half-life is different from isotope to isotope, but the general range is like 10 to the 14 to 10 to the 24 years. This is actually much longer than the age of our universe. If neutrinos satisfy certain property, for example, if neutrinos are their own antiparticles, then these two emitted antineutrino in double beta decay could collide each other, could just annihilate with each other, just like the positron electron annihilation before they leave the nucleus. In this case, we do not have anything that could carry away an indefinite amount of energy. Now, if you measure the energy of these two electrons, you will find a tiny little signal peak at the high energy end of this normal two neutrino double beta decay spectrum. So this is what we call a neutrinoless double beta decay, and it basically is one of the most important topic in rare event search in 2023 nowadays. So double beta decay is very interesting because, first of all, this process violates lepton number by unit of 2. And as you know, that lepton number is an accidental symmetry in the standard model, but it has never been observed to be violated. Because of this, it can also explain the matter-antimatter asymmetry in our universe. And it would basically, in summary, it would change our fundamental understanding of the particle physics. So this process has not been observed yet, but currently the best we know is that it must be longer than about 10 to the 26 years. So this is even orders of magnitude slower than this double beta decay process, which has already been very slow. So another important topic in rare event search is dark matter, which is probably a little bit more famous. So I guess many of you have seen this very famous chart where it says that the ordinary matter that made of the universe that we live in only constitute about 5% of mass in our entire universe. So the rest, like 27%, are dark matter, and the rest, like nearly 70%, are dark energy. So the evidence of dark matter existence has been plenty because we can see it from the galaxy rotation curve's velocity. So basically, if without dark matter, our galaxy wouldn't be rotating as fast as we observe them right now. And also, you have plenty of evidence of dark matter from like gravitational lensing effect, from the large-scale structure formation, and also the cosmic microwave background. So there has been many dark matter candidate particle that has been proposed. So some of the famous ones, including the WIMP, or weakly interacting massive particle, and also axion particle, and a lot of the other kind of candidates. The only thing is that none of this particle has been observed on any laboratory on Earth. So in this talk, I'm mainly going to be introducing this WIMP, weakly interacting massive particle, and I will omit the rest of the dark matter candidates. So basically, WIMP, we consider WIMP as kind of like a halo that's flowing through our universe and is constantly penetrating through our body, all the time. The only thing that is kind of like neutrino, that it only rarely interacts with us. So the interaction between WIMPs and the nucleus is really like kind of playing these billiards. So you have a billiard ball that hit a nucleus. So this nucleus is undergo what we call the nuclear recoil, and then this WIMP is going to be scattered away. So this nuclear recoil is really the signal we want to search in order to discover this WIMP dark matter particle. So what makes rare event search? What makes searching for neutrinoless double beta decay and WIMP dark matter really hard? That's, of course, by its name suggests, is extremely rare. So let me use neutrinoless double beta decay as an example. So we have not seen neutrinoless double beta decay at a half-life of the order 10 to the 26 years. So the next generation experiment typically aims at reaching to a sensitivity of 10 to the 28 years. So that's about 100 times improvement compared to our current generation neutrinoless double beta decay experiment. So I just want to give you a sense, because all of those numbers looks very large, but it probably doesn't make too much sense. So this number, so if neutrinoless double beta decay actually happens at a half-life of 10 to the 28 years, that means we will be able to observe about 3 to 4 events after 10 years of data taking over like a ton of material. So that's a very long time and a very small number of events. So this means we will be having about 1 event every 2 to 3 years. And we basically, in rare event search experiment, we cannot bear the stake of missing a single event, because that means if we miss this event, we need to wait for another 3 years. And if you miss 2 events, you need to wait for like a 6 year, which is almost like you're getting a PhD. So basically, we need an ultra sensitive detector to capture like every single event that we can take within our detector. But now there is another kind of a controversial, contradicting point, which is that as our detector gets more sensitive, we also collect lots of events that are actually not neutrinoless double beta decay or nor WIMP dark matter. So now this rare event search really become kind of search for a needle in a haystack problem. And this problem really depends on how large of a haystack do I have. For example, if I have a needle that falls into this haystack, I mean, I don't even want to spend my time searching for it because I know I'm losing this needle forever. If I'm having my needle in this haystack, well, it's still very hard and I still probably couldn't find it, but it's just like maybe 0.1% more probable than like finding a needle in this haystack. But if I have my needle in just this very small haystack that's just on the top of my palm, then, you know, it's still going to be pretty hard, but if I spend like half a day or something, I think I will be able to find the needle without too much problem. So besides, you know, having the signal of the needle is also very important to reduce the size of the haystack that we have in our detector. So this is to reduce the background that we will see in our detector. So the Cohen ring experiment, which was performed in 1950s as a rare event search experiment, as I said, the interaction, the needle is still very small, but the haystack, the background is nearly background free because we can look for these coincidence signals between neutron capture and pair annihilation. So that's why this experiment was very exciting back in 1950s, but nowadays no longer exciting. So for neutrinoless double beta decay, we have this very tiny signal as a high energy end of the 2 neutrino double beta decay spectrum. But beside that, we also have a lot of naturally radioactive and cosmic ray generated background that's kind of hovering above the signal like this purple kind of ocean. So it's usually a flat spectrum, but sometimes it has some kind of internal structure. So this is basically the background we need to fight for in neutrinoless double beta decay experiment. And the similar logic falls for the WIMP dark matter search. So in the WIMP dark matter search, our signal is a nuclear recoil, but we also have a lot of what we call the electron recoil. For example, this naturally radioactive or cosmogenic photons can scatter off of the electron, which creates another recoil signal. So those are the backgrounds that those are the haystack that we really need to reduce its size. And controlling background is of unparalleled importance in rare event search experiment. So how can we achieve all of that? So as I said, we have WIMP and neutrinoless double beta decay on the left side, and we want to extract some physics on the right side. So basically what we can do is that we first need to build a radiation detector, which serve as kind of like a magnifying glasses that help us finding the needle. And we also need an AI ML algorithm that acts as a forklift that can help us removing the haystack. So in the following section, I'm going to try to combine these two by each pairs. Among 3 different experiments, I'm going to tell you how each radiation detectors are going to work and how AI ML algorithm can be used to help those radiation detectors. Now let's enter the second part, which is the fast part. So the first experiment I want to talk about is the so-called Kamlan-Zen experiment. It is a monolithic liquid scintillator detector built for the search for neutrinoless double beta decay. So this is mainly a US, Japan, Netherlands collaboration, and we have about 70 collaborators from about 14 different institutes. I work within the so-called MIT BU analysis group, and here is a photo of our smaller group within the Kamlan-Zen collaboration. So Kamlan-Zen is a very large detector. As you can see, here is a person standing on top of our detector. So our entire detector is like a height of several, it's like an entire building. But it's really nothing more fancy than like a camera as you use every day. So the 2 of the most important components of the Kamlan-Zen detector, first is a liquid scintillator, which is analogous to the flashlight of your camera. So liquid scintillator is kind of like an organic chemical. So when a particle enters liquid scintillator and deposit energy, it's going to emit a lot of isotropic light. Isotropic just means the same in all directions. And those lights are going to be propagated outward to this so-called inner detector PMTs. So the inner detector PMTs, I have a picture here. They look like a light bulb, but they are actually detecting light instead of emitting light. So they are really analogous to the lens of your camera. So those scintillation light will be captured by those inner detector TMTs, those 1800 inner detector PMTs that's spherically surrounding our liquid scintillator detector. And then by analyzing those signals, we'll be able to understand what kind of physics event that happens in our detector. So in Kamlan Zen, we also deploy an additional what we call the bloom, which is which is what we call the inner bloom, and is a 25 micrometer thick transparent nylon film. So within there, we perform a process called xenon loading, where we load a double beta decay isotope, xenon 136, inside the liquid scintillator inside our inner bloom. So this is what we call a xenon liquid scintillator within this small inner bloom region. And this is basically the target where we want to take a picture of with our liquid scintillator detector. So now let's take a look at the taste stack. So basically the major background sources in Kamlan Zen, given this configuration, are the background that's generated within this xenon liquid scintillator, and also the background generated from the film of this inner bloom, as I discussed earlier. So now let's take a look at how the data produced by Kamlan Zen look like. So when a particle deposits energy in the liquid scintillator, let's say it generates 10,000 photons and it travels outward, but only about 2,200 photons will actually reach the surface of the PMT. The rest of the photon will just escape from the fissure between your PMTs and also some of the other structures. So this 22% correspond to what we call the photo coverage of the Kamlan Zen detector. So among those 2,200 photons, only about 500 of them will actually produce a signal, or what we call the photoelectron, because your PMT is not 100% sensitive. So the probability that an incoming photon will actually produce a signal in your PMT is what we call a quantum efficiency. So, and our quantum efficiency is only about 23%. So only if a photoelectron is produced can you say that your PMT is triggered and can we read out information from our PMTs. So now let's take a look at what kind of information we can read out from a trigger PMT. So basically, there are 5 pieces of information. The first 3 pieces is the PMT locations subscribed using the spherical coordinate r theta phi. And also we have the time that the PMT triggers and also the charge that was deposited into the PMT. So the most easy information you can read out is that if you add up the charge of all the trigger PMTs, it's going to be proportional to the energy of the incoming particle. So that's pretty easy. But let's put that aside for just a second. We can also read out the time of all the trigger PMTs, and we can plot them into a 1D histogram, as you can see here. So this is what we call a scintillation time profile. So the shape of this 1D histogram actually would reflect the location of the particle that's depositing energy in your liquid scintillator detector. However, the scintillation time profile does not contain all the information that our trigger PMT provide us because we haven't been using the position of these trigger PMTs. So we have been using this r theta phi information. So in order to use that, let's try to pull out each bins of our scintillation time profile, and let's try to open up the surface of our sphere and plot each of the trigger PMT as a dot on this so-called theta phi spherical map. So basically here I'm showing you 4 different theta phi sphere map at 4 different snapshots as labeled by those purple kind of bar. And basically, this is going to give us what we call the spatial temporal data, which is a time series of 2D images projected onto a sphere, or you can think of it as kind of like a spherical video. So this is the data that we need to deal with using machine learning algorithm in Kamlan Zen. So how can we deal with it? So let's first split them into 2 parts. So let's first deal with a time series of 2D images. So to deal with this kind of data, we actually can use a so-called convolutional long short-term memory or COMP-LSTM network, which is basically kind of like a recurrent neural network. So the idea is that you have a time series of 2D images, and what you can do is that you can feed them one by one into this RNN structure. So when you feed in the first frame, the RNN is going to give you a first hidden state, which contains the information from only the first frame. When you then feed in the second frame, the RNN is going to produce a second hidden state, which contains information from both the first and second frame. So you can keep feeding in more and more frames. And when you reach the last hidden state, it's going to essentially contains information from all these frames. And now let's pull out all these intermediate hidden states and also the last hidden states and feed it into a so-called attention mechanism. So the idea of attention mechanism is based on a so-called score function, which produce like a scalar similarity between each of the intermediate hidden state hi and also the last hidden state h last. We can then feed this score into a softmax function to make sure that they sum up to 1. So we essentially turn it into a so-called attention weight. And the last step is to perform a weighted sum between your attention weight or attention score with each of the intermediate hidden state to produce a context vector. So basically, after you feed in your spatial temporal data into this conv LSTM plus attention mechanism, you should produce a context image which summarizes all the important information that's happening in your spatial temporal data. So the second thing we want to address is what happens when your data is projected onto a surface of a sphere. So why is this important? So let me give you a very simple example. Suppose we have a circle that lives on the surface of the sphere, and the circle is facing up like this. Now, if I open up my theta-phi heat map, like what I showed earlier, your sphere is actually going to look like a straight line, as you can see here. However, if we rotate the circle a little bit, and now if this circle lives on the belly of your sphere, and you open up this theta-phi heat map again, then now this circle actually looks like an actual circle. So basically, if you train your machine without telling it this kind of a symmetry within your spherical data, the machine is basically you are telling the machine that this straight line is the same as this circle, which doesn't make any sense. So to address this problem, we leverage a model called a spherical CNN. So the spherical CNN can be kind of explained in analogy with a normal convolutional neural network. So we know in a normal 2D CNN, we have a 2D flat input image, and we scan a 3x3 filter throughout the surface of this 2D image, and the output feature map is also flat. So in spherical CNN, you have your filter is now covering the entire surface of your sphere, but it's only covering it from a given angle. The scanning process now becomes a rotating process where you rotate through all the possible configurations in the error angle, and for each error angle, you record down a value, and then that forms your 3D feature map. So that's why the feature map is 3D, which spans the error angle instead of a 2D feature map. So this basically, by doing this, we are basically viewing this spherical image from both the angle where it will look like a straight line and from the angle where it will actually look like a circle. So combining all this, we have ComNet, which is an integrated spatial temporal neural network. So our spatial temporal data first got fed into a series of attention conv LSTM layer, which produces this context image. And then we feed this context image into a series of spherical CNN layer to address the SO3 symmetry and the rotational invariance. And this will produce a 128-dimensional feature vector. And lastly, we feed this feature vector into a series of fully connected layer to produce a single value, which is what we call a ComNet score. So basically, after training, a higher ComNet score means this event is more signal-like, and the lower ComNet score means this event is more background-like. So monolithic liquid cylinder detector has been at the heart of many great discoveries in neutrino physics, but it lacks the ability of reviewing the particle track like what we can do in time projection chamber detector and highly segmented liquid cylinder detector. For example, Dune is a liquid argon TPC. When a particle enters the Dune detector, it can produce this very beautiful track which tell you like some of the important properties of the particle. It also lacks the ability of extracting useful information from event topology, like what a Cherenkov detector can do. So enhancing monolithic liquid cylinder detector with the capability to discriminate between different event type based on tracking and or event topology would be a revolutionary advancement in this detector technology. So ComNet, leveraging all of those symmetries within your spatial temporal data can actually achieve that. So basically in ComLAN Zen, when we are searching for neutrinoless double beta decay, our signal are what we call the strictly single vertex events, where all the energy deposition happens almost immediately at a very localized location. However, most of our background are actually what we call the closely spaced multi-vortex events, where part of the event energy is deposited by a photon cascade that slightly alters the event topology. So this photon cascade usually only happens at less than a few nanoseconds later. Therefore, we used to consider that they are indistinguishable from each other. But actually, COMNETs, leveraging those symmetries within your data, can actually distinguish this from this. So we can actually see it from interpretability study we perform on COMNET. So to understand that, let's invite back our old friend, which is attention score. So attention score is a probabilistic flow point number COMNET assigns to different part of a liquid scintillator events. So a high attention score means this part is very important when making the decision, and the low attention score means this part doesn't really matter when making the decision. So based on the attention score of this bismuth 214 background rejection, we can see that it pays attention to both the primary electron vortex and also the later secondary gamma vortex. So COMNET would be able to capture this tiny alteration in event topology to efficiently reject like almost most background in COMLAN, which is great. So while accepting about 90% of the signal, COMNET can reject 27% of the xenon liquid scintillator background and nearly 60% of the film background. So the increased rejection of the film background also allow us to expand our fiducial volume from 157 centimeter to 166 centimeter, resulting in a 17.7% gain on our experimental exposure. So now let's see what kind of new physics that COMNET can enable us to do. So as I mentioned, before we apply COMNET, our exposure is 970 kilogram. After we apply COMNET, our exposure goes up to 1142 kilogram, corresponding to a 17.7% increase. And if you were to buy more xenon 136 at the beginning of the experiment to reach the same exposure increase, you would have paid $2.5 million more. So it can directly save you some money. So in COMLAN Zen official result, we actually apply COMNET to only a high background period. And this is actually a very conservative use of this very powerful model, but it still whittle a critical background that passes all of our traditional background rejection method. And this leads to the official COMLAN Zen 800 limits at 2 times 10 to the 26 years. We also combine this limit with our previous phase to reach an even better result at 2.3 times 10 to the 26 years. And this xenon neutrinoless double beta decay search represents the world's most stringent limit on the so-called effective Majorana math, which is a theoretical number. Lastly, if you apply COMNET to all the data instead of only the high background period, you can further increase the half-life limit from 2 to 2.7 times 10 to the 26 years, corresponding to a 35% boost on your performance. Okay, now I want to switch to the second experiment, which is the legend experiment. So the legend experiments aim to develop a phased germanium-76 based double beta decay program with discovery potential at half-life beyond 10 to the 28 years, using existing resources as appropriate to expedite the physics result. We are a collaboration of about roughly 56 institutions and 270 scientists, basically mainly from the US and Europe. So Legend uses a different detector technology, which is high purity germanium detector array. So to explain this, I first want to explain it using the scope of a light emitting diode or LED. So I assume most of you have seen a LED before. If you haven't seen it before, look at your computer screen. Now you have seen it. So basically, LED is a semiconductor device which produces this so-called depletion region. So I don't want to go through all the semiconductor physics, but basically how it works is that the depletion region has no charge. But if you apply a voltage across it like this, using a battery, it's going to be recombining what we call the electron holes, which then emit light. So what we do in high purity germanium detector is that we reverse the direction of this battery. So if we do that and we increase our voltage, we can actually expand the depletion region to cover our entire detector. And also germanium-76 is by itself a neutrinoless double beta decay isotope, so that we can basically use it to make our detectors. The only problem with this germanium detector technology is that each detector cannot be made very large. So currently the largest detector we can make is about 4 kilograms and is like the size of my palm. So In order to overcome that, we actually put several germanium detectors together into what we call the detector array, as you can see on this bottom plot. So when a particle deposits energy, let's say when a neutrinoless double beta decay event deposits energy in the germanium detector depletion region, it's going to create a lot of charge. This charge then drifts under the electric field into this point contact. So if you read out the voltage signal at this point contact, what we will see is this kind of step-like waveform in the charge space. So you can also perform an derivative. You can also differentiate this waveform and convert it into a current space. That's this purple waveform. Most of the background that happens in germanium detector is a photon that scatters multiple times. So in this case, if a photon deposits energy in multiple times, and it's also going to create a lot of charge and they drift into this point contact. But because they reach this point contact at different time, you will have this kind of multi-stage-like waveform, as you can see on the bottom plot. So on the top, we have what we call the single-side event, which is a neutrinoless double beta decay candidate. And on the bottom, we have this multi-side event, which is mostly background. So in Legend, we also develop a lot of pulse-shape parameters which help us distinguishing signal from background. For example, if we read out the maximal amplitude within the current space, this can help us rejecting multi-side background. If you read out the height of your entire waveform, that is proportional to the energy of the incoming event. If you read out the tail slope, this is also helpful for rejecting another type of background called surface background. And lastly, if you read out this part of the waveform, it tells you how long does it take for the waveform to drift from its energy deposition to the point contact. Okay, so basically in Legend, we develop a machine learning model called Legend baseline model. So this model is actually much easier than ComNet because in Legend, we only have a 1D time series instead of spatial temporal data. We just use a normal long short-term memory, which is a recurrent neural network, and we hook it into the attention mechanism to achieve different analysis tasks. So this model can be used to achieve background rejection. Basically, we can just hook a fully connected neural network on top of it to identify and reject the multi-site background that I mentioned earlier. And another advantage is that this model is interpretable because the attention score, as I explained earlier in ComNet, will allow students to see where the Legend baseline model is paying attention to make decision. For example, when this model is used to reject this multi-site background, you can see it's actually paying attention to this multi-siteness within your waveform, which is very nice. So one of the projects we want to do is to improve the Legend baseline model using some more advanced machine learning algorithms. So basically, the idea is that we have some prior knowledge of this waveform, which tell us which part of the waveform is important and which part of the waveform is not. So when we are rejecting this so-called multi-site background, we know that the waveform, the rising edge, the blue region, and the upper turning edge, which is the red region, is very important in terms of rejecting the background. But the tail region, the orange region, is actually irrelevant. And the baseline region is even more dangerous because it has a potential to create a bias in our classifier. So we actually want our model to only pay attention to this region without paying attention to the region that are either irrelevant or it could introduce bias. So to do this, we actually leverage a novel machine learning model called feature importance supervision. So the idea of this model is just feeding different versions of masked waveforms into the Legend baseline model. So basically, when we feed in the raw waveform, which contains all features, it should give me an accurate output. If I feed in the part where I mask the unimportant part and only feed in the important part, it should also give me the accurate output. If I do the reverse, if I mask the important part and only feed in the unimportant part, the model should be uncertain. It should not know whether this event is a signal or background. If I feed in important part from randomly sampled unimportant part, it should give me the same output as feeding in the important features only. And lastly, we want to perform a supervision on our attention score. We want to tell the machine, hey, please only pay attention to the rising edge and upper turning edge, which contains the important information. So each of these will create a loss, and we just add the loss together and we optimize all the loss simultaneously. So here is some preliminary results on the feature importance supervision work. Basically, we are trying to guide the machine learning model to be right for the right reason. So we first design what we call the bias data set, where we select a data set to test for the energy dependency bias. So if we have a classifier that is biased, then we will have a non-trivial classification power on this bias data set. And if we have an unbiased classifier, we should not extract any useful information from this data set. For example, when we ask it to classify, it should just be kind of like flipping coin. So we can look at this receiver operating characteristic curve, and we can see that without feature importance supervision, our RNN model or the legend baseline model is extracting a meaningful classification power. But after we add feature importance supervision, it becomes the area on the curve is just 0.5%, which is just like coin tossing when making classification decision. So FIS can actually help us removing bias in our algorithm, which is great. And then we apply the same algorithm to reject background. So we can see that our RNN plus FIS model is actually reaching a pretty good performance. Our RNN without feature importance supervision is doing even better. But now we know that this better performance is actually because of a bias, and that's something we actually do not want in our classifier. So the last experiment I want to quickly go through is a xenon N-town experiment, which is a two-phase liquid xenon TPC for WIMP dark matter search. So in xenon N-town, we are really a global collaboration with like many different institutes and nearly 200 collaborators. So xenon N-town is a two-phase TPC. So by two-phase, I mean it has a liquid phase, which is on the bottom, and a gas phase, which is on the top. So unfortunately for this one, I do not have a nice analogy to explain. So you will have to hear my boring explanation about how it works. So when a particle enters this liquid part of the two-phase TPC, it's going to create what we call S1 signal, and it's going to create a lot of ionization charge. So this charge then drift in the electric field, and when it hits the liquid xenon boundary, it's going to undergo something called electroluminescence effort, which will produce another larger signal, which is the S2 signal. So both the S1 and the S2 signal will be captured by two panels of photomultiplier tubes or PMTs on the top and the bottom of your time projection chamber. So in this case, basically the data we are getting is also a spatial temporal data. But since now our detector is just two flat PMT panels instead of like a spherical PMT, so our spatial temporal data is actually a 2D flat video instead of like a 2D spherical video. Okay, great. So I will just keep going. So the xenon data, as I said, the xenon N-town data, as I said earlier, is a spatial temporal data, is a 2D, kind of like a 2D flat video. But because in Xenon, we have a huge amount of, we have a very high data flux. Basically, the processing pipeline does not allow us to save our data in this original spatial temporal form. So basically what we have to do is that we have to save different like kind of like squash version of our data. So one is to squash along the time dimension where we lose all the time information and we save our data in this kind of 2D image, as you can see on this plot. And the other is to squash along the XY dimension. So we lose all the positional. Okay, I think, let me share again. Okay, yeah, so basically we can also squash along this XY dimension where we lose all the positional information of our PMTs, but now we just have a 1D waveform. So basically on the top, we have the hit pattern, and on the bottom, we have the waveform, which is a 1D time series. So I have been working with my student Min Zhong at UCSD to build two classifiers that can work on signal background classification on both these two type of data. So for 2D images, of course, we use a normal convolutional neural network for image analysis. And on the 1D time series, we are actually using a recurrent neural network plus attention model, as I introduced in the previous part for the time series analysis. And both of them actually produce a pretty good result. So you can see here we have the raw curve on top for the CNN classifier and the raw curve on the bottom for the RN classifier. So we can see that the CNN is rejecting about 46% of background while accepting 90% of the signal. And meanwhile, the RN is rejecting about 62% of background while accepting 90% of the signal. The real interesting things happens when we plot the CNN score and RN score together onto this kind of 1D scatter plot. So we can see on both plots, we have a region where the CNN, where one of the network is performing well, but the other network is performing not so well. So this is what we call the confusion region. So for example, on the signal events, ideally both networks should give you a very high score. But here is a region where the CNN is giving you a high score, but the RN is not. And a similar region exists on the background rejection, where both should give you a low score, but the CNN is actually giving you a high score. So our next step on this project is to combine the CNN and RN to classify these confused events better. And this is the direction we will go in the future. So now I'm reaching the end of my talk, and I want to talk a little bit about the outlook of what I want to do within the scope of A3D3. So that is using fast machine learning to further help rare event search. So first, if you want to do a real-time machine learning, you will need some hardware support. So luckily in Kamlan Zen, we have this new electronics that we plan to develop for the Kamlan 2 Zen experiment. So the primary goal is to digitize waveform during a chaotic period after muon passes to better reduce the long-lived spoliation product and stream data and large memory. And it includes basically a streaming data capability and a large memory buffers. But the main thing on this board that I'm really interested in is that it has this so-called radio frequency system on chip, RF-SOC, which is basically a FPGA chip with a programmable FPGA chip with a radio frequency module. So basically, this will allow us to perform different kind of machine learning algorithm on the FPGA chip. And this is something I'm really interested in working in the Kamlan Zen experiment. And for the other experiment like Legend, for some of the other neutrinoless double beta decay experiment, I think we are also planning to use this RF-talk technology in our data acquisition system, which is very nice. So I think another opportunity lies in the low energy region of our data taking. So here I show you a spectrum of the Majorana demonstrator experiment, which is a germanium detector experiment for neutrinoless double beta decay. So you can see if we are looking at this higher energy region at like 2000 keV, as I mentioned, the event rate is very low. It's like a few events. It's like a few events every 10 years. But if you move lower into this energy, you actually have an exponentially increasing event rate. Remember this plot, the y-axis is in log scale. So you can see at low energy range, we have a significant more amount of information than the high amount of events than the high energy region. And also, as you approach this low energy region, you have a lot of electronic noise. So I saw some of them on this upper right plot. So basically, this is going to kind of saturate your event buffer and stop you from reading out a lot of very interesting physics that happens at low energy. So if we can develop an AI trigger on our board, which allow us to dip even deeper into our energy while rejecting those low electronic noise events, so that's going to be very useful for us to search for some physics other than neutrinoless double beta decay. So the last thing I'm interested in doing is a real-time AI analysis. So for those rare event search radiation detectors that I discussed today, we'll produce some data stream and we use some data acquisition board to analyze it. So, and the traditional analysis is basically an offline analysis where we store our data somewhere and we analyze it to produce some of the important physical information like energy, position, particle type, and detector response, etc. So one thing I'm very interested in is it possible to use some online learning technique to kind of bring this information onto the FPGA chip? So instead of doing some offline analysis, we perform some kind of online analysis, which allow us to spit out the energy, position, and particle type of each of our events right at this FPGA chip. So that will be something that's very exciting for the rare event search experiments. Okay, so now I reached the end of my talk, and I just want to give you a very quick summary since I'm running a bit out of time. So, so the slow part, I introduced that rare event search provides a unique window to unravel the mystery of neutrino and dark matter. High sensitivity and low background is required for this kind of search. So on the fast part, I discussed 3 radiation detectors and 3 machine learning algorithms that we kind of customly designed for each of the detectors. And lastly, for the fast for slow part, I discussed about the hardware component, which is the RF-SOC system for Kamlan Zen experiments, and also the algorithm I'm interested in working on under the scope of A3D3. So lastly, I would like to thank you for your attention. And if you are interested in collaborating to do AI in real event search, please feel free to send me an email. So thank you. So Kate said she cannot unmute. Maybe someone could unmute her.
Okay, now I seem to be unmuted. We have to go into lockdown mode. Yeah, sorry about that disruption. I guess we're going to have to try to upgrade these seminars to be a little more carefully checked attendance. But yeah, thanks very much, Aobo. That was really a great seminar. Really a whole bunch of different possibilities. I guess we're open for questions.
I guess people cannot unmute, so please raise your hand.
People can unmute. Yeah, maybe can raise hand.
But I actually think this is a good.
Happy has a hand up.
Yeah, I think they can unmute now. Sorry.
Okay.
I had unchecked everything, and then I enabled it back now that we have the waiting room thing.
Okay.
Yeah, I just had a question on like in terms of the architecture, I guess, of I guess I was wondering in terms of the symmetries that are inherent in some of the architectures you were talking about, is it capable to learn kind of like asymmetries or you know, kind of irregularities or something in the detector that may not be symmetric, like spherically symmetric?
Yeah, that's a very interesting question. Actually, sorry, I think I need to reshare in order to flip slides. So yeah, so let me go back to here. Where is here? Yes. So basically, I want to say that so the idea that we incorporate this symmetry, or you know, in the sometimes we call it inductive bias into our neural network, and what it actually learned is it's gonna become sensitive to some very tiny asymmetry in our event. So for example, traditionally in liquid center detector like Hamlan-Zen, the data that we receive is supposed to be isotropic. So that means the same amount of light in every direction is like spherically symmetrical. But this effect, this closest space multi-vertex event is gonna slightly just disturb this kind of spherical symmetry, and it's gonna make it like slightly asymmetric from like a purely isotropic signal. So the network, after it understands this kind of spherical kind of behavior of your data, it can actually become sensitive to this like very tiny like a anisotropy. And we use this to kind of distinguish signal from background. So I think this is actually making your model to some extent more sensitive to the asymmetry in your data. I mean, of course, you need to train it with a correct data. For example, if you want to learn some kind of asymmetry, maybe your signal is now like a symmetric data, and your background is some data with slight asymmetry. And if you train it this way, then it will be able to learn the small asymmetry. Yeah.
Okay, I see. Thanks.
More questions or comments? Okay.
Sorry, maybe I had one other question. Oh,
Go ahead.
actually, like I can let Janina go first, and then I can ask mine.
Oh, Janina. Yeah, Janina.
Hello. It's very interesting talk.
Thank you.
I wanted to ask on the germanium.
Oh yeah, please.
Which sampling rate are you using for the pieces? And is there a dependence on the sampling rate for the effectivity of the neural network?
You mean sampling rates of our data acquisition system, or like you mean this waveform, or?
Yes, of the waveform, like how many points you have actually in the waveform to get this rise.
Yeah, so you can see here on the x-axis actually label the time. So you can see the entire rise is about maybe 500 nanosecond. And I think our sampling rate is every 10 seconds. I mean, it's different from detector to detector, but in one experiment, we have like 10 nanosecond sampling rate. In one, we have like 16 nanosecond sampling rate. So it's in that ballpark, basically, yeah.
Ah, okay. So that is also what you need. So if you would have much less points, probably that would not work so well to distinguish.
Yeah. I mean, of course, I think if you have a higher sampling rate, then you are basically you basically include more features, right? Like a local vehicle, for example. But also, sometimes higher sampling rate means you are capturing better of the noise that's happening in your electronics. So I think there are some, up and down effects. But I think the thing that's if you have a higher sampling rate, it's always easier to downsample. But if you have a lower sampling rate, you cannot sample back, right? Unless you are creating some like you're doing some kind of interpolation. So yeah, I think a higher sampling rate is generally, I would say, preferred. Yeah.
Okay, thank you.
Okay, Javier, you had an additional question?
Yeah, I guess I was also wondering in the fast part, what is the kind of like latency requirement or overall, yeah, like what is the latency or throughput requirement for running these in real time? Yeah.
Do you mean the AI trigger or the AI analysis?
Yeah, I guess either. Yeah, either. Yeah, like how should I think about it in terms of the like time constraints for either use case? Yeah.
Yeah, so first of all, I have to say, sorry, I'm not very familiar with the latency because, in real event search experiment, our event rate is pretty low. So we rarely care about like latency like you guys do. So I would say for the real-time analysis, AI analysis, the latency requirement is really not that important because we just try to make this value comes earlier in our analysis chain. Because if we do our offline analysis, maybe you will not get your energy position and particle type until after like weeks after you take data. If you can make this like seconds after your data goes into your board, then that's already a very big step for us. So I think it's not that important for this AI analysis. For the AI trigger, I would say is much more important because a trigger actually decides, which event we want to say, which event we want to discard. So for this one, I think we want the machine to make a very quick decision. But even given that, you can see here our event rate is not that high. So it's like 1,000 event per bin, per energy bin. So I guess, of course, I don't have a number, but my general kind of message is that I think our requirements is much lower than what the LHC and the Dune will require for their latency for their system to be. Yeah.
Okay, but like order seconds is kind of the target. Okay, but yeah, it makes sense. Yeah.
You actually might want to think about for real-time supernova triggering. You do want to have a low latency.
Yeah, actually, that's a very good point. I think Kamlan-Zen experiment has already been hooked into the snooze network.
Yeah.
So for the other experiment for Legend or Majorana, because our detector is pretty small, I'm not sure if it's a good candidate for supernova, but I think we have someone in our collaboration who is looking at this direction. Yeah, if we have supernova, then that's a different story because your event rate all of a sudden become very high. And yeah, in that case, a low latency would be very helpful.
Okay. Oh, Ryan.
Hi there. Welcome to UCSD. Belated welcome.
Thanks.
My question was more on the RF SOC. Are you using that now? And is that how are you using that? I guess are you actually using the onboard processing there, or are you just using it as a ADC right now?
Yeah, so basically the Kamlan-Zen experiment is currently in a phase called Kamlan-Zen 800. So we are planning to stop our data taking, I think, pretty soon, and we are going to build a brand new detector called Kamlan-2Zen. So in the current generation, Common Zen 800, we do not have this RF sock. And for Common 2 Zen, the idea is to replace all of our data acquisition board with this RF sock powered board. So we are currently kind of benchmarking these boards and try to understanding the performance of these chips and also the other parts. So I would say we haven't really been using it to take data, but this is going to be implemented pretty soon. Yeah.
Okay, great, thank you.
All right, more questions or comments? Okay, if not, well, thank you very much again, Aobo. That was really a great survey, and we look forward to having you as part of A3D3.
Thank you. Yeah.
All right.